Good evening.
Good evening.
Okay, and Linda, it looks like that workaround worked.
Yep.
Excellent. Uh, and Linda, I also, and this happened after I suggested this and sent it to you, I sent another copy of these two PDFs to everybody in both classes. Okay. So was that one of us?
That was somebody.
Okay. Anyway, and we do have some students here, right?
Yes.
All right. So what I would suggest that the students who are here can do is go to your COD email, and maybe you want to do that out of a different browser or something, just so you can come right back here. But we're going to start going through these. But these notes have been sent to you by email from Blackboard. Blackboard had a problem tonight where they were saying that we couldn't load our things, but Linda cleverly came up with a way to work around this. So anyway, we're going to start doing this. So anyway, Linda, let's go to the, oh wait, I can do this too. Maybe I'll go to the, well, Linda advanced the slide, that's good. Now, here's what we're going to be doing tonight then, my students. We're going to have a final note on Snell's law. And that's not going to take very long, but then we're going to focus on the final reviews. And we're doing that tonight because students wanted to do that tonight, and we're also going to do some of that on the next night, Thursday. And Linda will be, at least we hope she will be, and when I say hope, I think if it's technically possible, she will be doing this. We are recording this, and so these will be posted for people to see. I am going to be publishing some additional videos, but I think the additional videos are going to be limited the rest of this week to posting some LSA solutions for you all, so you have those. Now, I do want to make sure everybody is aware of that the Zoom final exams will happen 1 week from today, okay? And what will happen is there will be Zoom addresses and things like that. The VCM folks will be taking it from 6 to 7:50, and the net folks will be taking it with their assigned proctors. I already did email you the grace notes. So you do have that, okay? And we will be looking at the grace notes with Linda as well. Okay, now I need to think about what I was trying to say. Okay, the Zoom final exams will be 1 week from today, and I really encourage you one email says collateral 1 and the other one says collateral 2. They have different attachments. One of them is the attachment of the grace notes, and the other one is attachments of the slides, I think. Now, if I did screw that up trying to scramble around to get this there,
This is the study guide.
Thank you, Linda. Yes, there is a study guide. This is the study guide. So if I were you, I'd pay attention tonight, and but you certainly will do what you want to do. Okay, so this is part of the study guide. There's going to be more study guide. And again, I would encourage you to check because I don't think those are the same emails twice. Now, I could have screwed up, and if I did, I will send it to you again. But I think one of the emails had the grace notes attached. Okay, after this thing, I will send the grace notes then to you. And I was trying to get around because Blackboard refused to cooperate uploading stuff. Okay. Linda, you got anything you want to say?
I can actually send out the grace notes right now. So
Really?
if you guys give me a minute, then I can do that through Blackboard.
Okay, so Linda's going to send out the grace notes on Blackboard, and I was intending to do that. And so you'll have them, and this will be an email from Linda then that will have grace notes on it. Okay, let's see if there's anything else. Okay, so I guess this is questions and answers, and so everybody's just writing on this slide. So do you have anything else you want to say? And you don't have to write it here. You can put it somewhere else if you want. And well, no, why don't I go back and read what I was trying to read? The exams will be proctored. If you have any accommodations, you need to let me know as soon as possible, because your, I mean, the term ends and there's no things after the term ends. So you have to, do this in advance, and that shouldn't be a real problem for you. I mean, you have this week to get that done. There will be an answer sheet. That is the primary grading instrument. And I really encourage you to submit this the right way, because if you don't, it'll be very awkward and there's not a lot of time at the end of the term. So I would really, really focus on submitting the answer sheet, the right way. It will be password protected. You'll get that from the proctor. You will have an opportunity to submit a PDF of your work, and you will be using Excel or your on-screen calculator. And they're going to, and that's pretty much what you're going to be limited to. And they will know that you have grace notes too, and I will send the grace notes to the proctors as well, so they know what you're supposed to have. Okay. So Linda, are you back yet?
Yes, I am. The VCM people should already have it. The NET people will be getting it shortly. The email's just loading.
Okay, great. Okay, so that's going. Linda, you have anything else you want to say?
No, I think that pretty much covers it.
Okay, so now I'm asking the students in the class, and a number of you wrote comments here, and I think we dealt with all of them. I guess there's a question of how much will you curve. I think what I would encourage you to do is do your best on the exam, prepare well, and again, I know this is one of the first things I said in the term, but I think if you focus on learning material, the grades will take care of themselves. Anything else? Okay, well, certainly you can ask questions and things like that. Linda, let's do our traditional poll about how people are.
Okay.
I am going to answer the question.
Yeah, so since the grace notes are invalid files, then we sent them out via email. So check your COD email.
Okay, that's good. Some person found it. That was good.
Yes, the grace notes that were sent out will be the ones that you'll have during the final. And you will have to turn it in both the assessment tab and the PDF tab.
Yeah, and someone did ask the question about the about that. So there is a PDF tab or PDF upload area where you upload it. And Linda, maybe you can just remind me, but I have to talk to the Blackboard people to understand what they're saying about us using more than our quota to make sure that that all works. But I think it will. I mean, we will make it work somehow. You
can make a PDF just by taking a picture of it and saving it as a PDF.
And And we've been doing that all this term. We've done that on all the low stakes assessments. And so if you were turning those in, you should have practiced that a little bit. The best thing I think is to use, what is it called, Linda? And I don't know if this is the best, but it's called Office Online or something.
So you'll be submitting the PDFs after the proctoring is over.
The same way we did for the midterm, exactly the same way we did for the midterm. So if you can remember what you did on the midterm, then that's how it worked. Okay, exactly as it did on the midterm. And Jessica, I wasn't trying to ignore you, but Linda was, kind of answering those questions. So Jessica, are you still having a question? Are you good?
Yes. Now, can we print out the grace notes and have them with us, or are we not allowed?
Yes, you can.
Okay.
And what I plan to do is email you the exam. Yeah, and there's many applications you can use, to do that. I would really prefer it be a single PDF and not 50 different PDFs. And so some of the programs let you to do that, and that is a better thing to do. Jessica, back to your question. I will send you right before the exam. I will send you an email of the text of the exam. Okay, and so you will have that, and you will have an opportunity to print that off if you want to, or you can just look at it on the screen. Okay. You'll see actually the grace notes are very extensive, and so you I don't know what you'll want to do. Jessica, did I answer your question good then?
Yeah, that's what I just wanted to make sure, because it's like 35 pages, so I just wanted to see if I could print it out and have it next to me versus going back and forth.
You certainly can do that. Someone said that seems like a lot of work, and they probably, I guess, didn't really do this for the midterm. But that's what everybody was trying to do, and it's really pretty easy. We use it for all these classes, and now some of my students just refuse to do it, but the ones who cooperate find it's pretty easy to do. And again, we practice that on all the LSAs that we turned in, and so you can practice that. It doesn't take that long at all. And someone was asking, how could you do it if they're proctoring you on the file? I give you some time after the exam is over to send it up. Not long, but it's like 15 minutes, and that's plenty for you to be able to do that.
And we just send in the like our scratch paper, the notes that we use to figure out the solutions, correct?
That's the work that you can send in as the PDFs, yes. But there is an answer sheet, and the answer sheet is the main grading instrument, okay? So if you left the answer sheet totally blank, I would say you didn't have anything to say. So you really do want to answer things on the answer sheet, okay?
And that's going to be
on okay, and I've got two things going on here. Somebody's talking to me, Josh, so I'm not ignoring you. I'm going to call on you in just a minute, but I want to finish the discussion with the student who I was just talking to. And I'm sorry, I'm not 100% sure who you are, but please continue asking your question.
It's Jessica, sorry. So it's going to be like under the assessment where we put the other, just like the other test, we answer the questions in the assessment.
It'll be just like the other test, but Jessica, I'm reminding you and everybody else that the answer sheet was under the assessment tab. There's another tab that is called PDF upload, and that's where you upload the PDF to the other Blackboard tab.
Yes. Okay. Thank you.
Great. And Josh, I don't know if your question was the same, but I promised I would call on you, so I'm calling on you now.
Nope, question got answered. Thank you.
Oh, okay, great. Sometimes that happens. Okay, Linda, did we finish all these questions?
I think so.
Now, I was watching the poll, and there were there might have been four, I don't know, 3 or 4 people that, said they were struggling. Well, the fix to that is, at hand. You can really engage in these activities, you can attend my office hours. Linda has hours. Tom Topol has hours, and things like that. And in the Learning Commons, just in general, you can go in there and get help many hours a week. So I would really encourage you to, as much as you can, fix that. Now, if you're struggling because you're sick or your car doesn't work or something like that, you do have my sympathy, but I'm not in a situation where I can repair your car. So, but if you have issues that you're struggling relative to the course, there's a good way to fix that.
So I actually do have a quick question for everyone. Are you guys interested in having the GSGs next week? So that would be from 5 to 6 on Tuesday. Thursday, I don't see much of a point since it will already be done by then.
Okay. Oh, yeah, she's polling too. Okay. And I suppose this means, yeah, and you might be able to come or something. Now, Linda, you will get paid for these, right?
Yeah, I get paid for those.
All right.
But if nobody's going to show up, then there wouldn't be any point in having it. So just making sure you guys are interested.
Josh has a comment. Go ahead, Josh.
Okay, so the grace notes, will those be in with the test, like for the midterm,
Yeah.
or
Those
they'll
will be at the
included there as
end
well?
of the test.
Okay, because I just wanted, like you said, we could print them out, and I was also
Right.
toying with the idea of flipping back and forth on screens, but we can't do that. So, all right, cool. Just want to make sure they would still be there.
Yes, you can print them out.
Oh, I can. Are you recommending we print them out?
Honestly, I recommend you print them out just so you don't have to keep going back and forth between the problems and the grace notes.
All right, cool. Thank you.
And I was going to say that I probably wouldn't print them out, and me. Okay. So Josh, you do whatever works best for you, and everybody else do what works best for you as well. Sandy.
I know you sent out an email with your new Zoom address for evening hours. Is your
Right.
morning hours still the same, the Zoom address?
The morning and evening are different. I did send them both out, and they were in pretty recent announcements. It turned out they expired on different days, but if you look in the announcements, they're the most recent ones.
Okay.
So, but they're not the same. I think they're different addresses.
Gotcha. Thank you.
Okay, and Sandy, it looked like your hand went up again, but maybe it didn't.
No, I was just lowering it.
Okay, that's fine. Anything else? Okay, now Linda, let's begin then. And by the way, I am covering this final note on Snell's Law because it's important. Okay, so that's why we're doing this, and then we'll go into the review. Okay, so Linda, let's please go to the next slide. And Linda, maybe you can point or something like that. Now, we studied Snell's Law in previous videos, but one of the things that you've learned is there are different equations sometimes for different laws in ultrasound, and they're not really different physics, but they can be simplified or things like that. And it turns out that in ultrasound, you end up having a question that is sort of like this. The concern is not what's the ratio of the indices of refraction, but rather what is the speed of the wave in the different medium. So what Linda's pointing at here, this is called Snell's Law. This is a different interpretation of it, but it says that the sine of the transmission angle divided by the sine of the incident angle is equal to the speed of medium 2 divided by the speed of medium 1. Now, Linda's going to maybe go down to the bottom, okay, where it says, how do we identify medium 1 and medium 2? Medium 1 is defined as the medium to which the sound is currently traveling. So Linda's showing you medium 1 over there. So you see you got a wave that's coming in that yellow part, I guess, and it's going into the blue part. So medium 1 is yellow, and it's probably not going to be yellow on the test paper, but anyway, there's a medium 1. But then it talks about medium 2, and medium 2 is the medium into which the sound is entering, and of course that shows as blue over there. Okay, now what we didn't do is we didn't say, well, what is the incident angle and what is the transmission angle? So Linda will show us. Now the incident angle is where is it hitting the boundary. So Linda's pointing to the incident angle right there. And that's when is that ray or that wave incident on the boundary, okay? So that's the incident angle. And the transmission angle is the one that's in the blue, and that's the transmission angle. And again, when we go through the grace notes, you're going to see that you do have this, but it's written just a little bit differently. But still, this is the idea of this. And I don't want to change what I wrote just because now people are saying, oh, no, this is the grace notes. You can't change anything. I don't plan on doing it. But anyway, this is what happens. And Linda would tell you that this is telling you that the sine of the angle is proportional to the speed in that medium. That's what that equation means. Now, if you remember what happened before with the incidence of refraction, it was inversely proportional. So you see, it's kind of important. Now that is, and the reason I'm telling you this is because this is something that, and I've written the test already, this is on the test. So you want to say, yeah, I want to make sure I understand that. Now, Linda, I don't think we need to read what does sine mean, because I think you should know what sine means because we've been studying trig since, I'm going to guess, the first class where we did physics. But anyway, whenever it was. Now, it does say underneath there, and Linda, this is where it says although, and this is a lie. It says, although calculation using Snell's law are not required, I'm going to tell you, yes, it is required, because the problem I write, you're actually doing the calculation because you know what sine means. You know how to use the calculator and everything else. So that's not true. I am going to expect you to do that. Okay. Now, Linda, let's go over and read some of these things then on the in the other panel. So under what conditions will the transmission angle equal the incident angle? Well, recall the conditions for refraction. We talked about these. There's an oblique incident. Now, oblique means it doesn't come in at 90 degrees. And in fact, if it comes in at 90 degrees, you get, you don't get any of this stuff. But we're not coming in at 90 degrees. We're coming in at various angles. So it's an oblique, not 90 degrees incident, and there are different propagation speeds. Now, when you look at this first example that Linda has over there on the right, this is a medium 1 and medium 2 have the same index of refraction. They're the same thing. It's almost like that boundary really isn't even there, so there's no refraction. So those two angles are equal by geometry. Okay, so there's no refraction. And in fact, that's, I guess, what it's saying in the words here, so maybe I shouldn't have jumped over there. So refraction will not occur when the speeds of the two media are identical. The angles of incident and transmission will be equal, and the beam travels straight ahead. But that's if these two things are equal. Most times they aren't. Okay, so the next thing then, Linda, in the bold, it says, under what conditions will the transmission angle be greater than the incident angle? Well, the transmission angle will be greater than the incident angle when the speed in medium 2 is greater than the speed in medium 1. And I worked with one student in my office hours, and one of the insights that they came up with was, oh, gee, the measurement of these angles for Snell's law are always relative to the normal to the surface. So you see those angles, and maybe Linda will point that out, they're measured to the normal, which is the perpendicular to the surface. It's not any other angles. And sometimes that's very important. In fact, I guess I will say, I think that's always important in doing that. Okay, then the last one says, under what conditions will the transmission angle be less than the incident angle? The transmission angle will be less than the incident angle when the speed of medium 2 is less than the speed of medium 1. And you see in this case, the angle, the wave is being bent closer and closer to the normal, and in the one right above it, it's being bent further and further away from the normal. And so this is what's happening. And so that equation that Linda showed you up there at the beginning of this chart is an important one for you to understand, in addition to the ones that we covered before. And the reason I'm saying this is because I've written the test. I've already given it to Linda. Okay, do we have questions on this, or are we good? Okay, now except for publishing some LSA solutions, this is the last learning that happens. Maybe you're relearning things and stuff like that. Okay, Linda, now so we're finished with that. No one asked any questions. That's good, but that's an important thing. Okay, now, Linda, I think what we want to do is let's go to the next slide and see what it is. Okay, people have asked for a study guide. This is the study guide, and the study guide is a list of things, but in addition to a list of things, it's not a list of things, because we're going to go over examples over the next 2 periods of these kind of problems. And don't think that problem 1 is a conservation of energy problem and problem 2 is a boundary behavior of Snell's law, because these are shuffled up a little bit. But I did try to come up with a short phrase that talks about what is each of these problems about. And so that's the scope statement. And this, I think, is a very useful study guide. This, coupled with what we're going to cover today and next time in terms of examples and the LSA solutions, kind of gets you back to where you say, yeah, I feel good about all this stuff. Just to give you an example of what I was talking about, what wasn't here. Do you remember when we talked about prevalence and sensitivity and selectivity and accuracy of laboratory tests? Does anybody see that on here? And the answer is no. Now, the reason I covered it was because I'm supposed to cover it. So I covered it. I'm not testing you on that. So when you're studying just for the final, you say, oh, I don't have to study that. So we have these topics. Conservation of energy. We talked about 3 kinds of mechanical energy in this class. So conservation of energy, we'll do that, and we'll look at a problem with that. Now, the problems we look at are not the exact problems that are on the exam, but they were my really best effort to do that. And sometimes I grabbed the problem that was right next to the one that I asked on the exam. So in a
He does that a lot.
I'm sorry.
You do that a lot. So if these problems seem familiar, then I'd suggest going back to some of the previous PowerPoints and working through those problems.
Okay, so good. And Linda, thank you for jumping in. You always add value. That's great. Okay, boundary behavior of Snell's law. We talked about a bunch of stuff there. We'll talk about more of it today. And we talked about a little bit of it there. There's definitely a full problem on that. There's a problem on vectors, but I think the vectors problem is probably tied in with not just a raw vector problem. That's like a math problem, but it's probably tied into Newton's laws of motion, because force is a vector. So those 2 things are down there I think those are kind of together. Intensity and attenuation. That had to do with the bird problem where you said, how does things, that's my daughter's dogs. My daughter loves dogs, and she has 2 right now. She has had as many as 3. And that's her dog Ace, who's barking right now. Anyway, intensity and attenuation is the loss in signal. So those were the problems about dBs and logarithms and things like that. And again, we'll do some examples of that. Rectilinear motion is motion in a line. Range equation was the 13 microsecond rule that we talked about. Pressure and Pascal's principle, we talked about that. Pressure is perpendicular force per unit area. We talked about hydraulic problems and things like that. So we have a problem like that. Projectile motion is motion in 2 dimensions in a plane. I also mentioned density here. It turns out density is, I think, actually combined with a projectile motion problem together. But still, it's a concept that we want to make sure you're comfortable with. And then we have a thing that says frequency, velocity, and wavelengths. So there's a problem dealing with that. And you should know that the velocity is equal to the wavelength times the frequency. And that will help you when you get there. And we'll see that equation as we go along. Newton's laws of motion I've already talked about. Dimensional analysis and scientific notation is, one of the things that we'll be talking about. And there is a problem about Doppler shifts. Now, Linda will be counting those, and someone was showing me a question there, and I didn't read it while I was talking, so I have to go back and maybe look, or maybe Linda can, well, let's see, I will count. There are 11 problems, okay? And there's like, I don't know, 1, 2, 3, 4, 5, 6. In my COD email, oh yeah, someone asked where something was. Okay, so, and thank you, Joshua, for answering that. In fact, Joshua has answered several students' questions along the way, so that's good. There are 11 problems, right, Linda? I think so.
Yeah.
And there's 11 problems, and that means there is 110 minutes for the exam because it runs from 6 to 7:50, so it's 60 minutes, and 50 more is 100. So that's 10 minutes per problem on average. Okay. Okay. I'm not. I think that was a discussion amongst students, and it's okay. All right. So now what we're going to do is we're going to walk through this was part of the study guide, but now, Linda, we're going to walk through the Grace notes. Now, Linda, that's a different PDF.
All right. Give me 1 second.
Okay. Okay, so it's Grace notes, and then we start going here. And let's see, I can make this bigger, yes?
Yeah.
Let me think about how I do that. Let's see, bigger.
So click on the little sheet of paper with a magnifying glass in the upper left-hand corner.
All right, so I'll just make it bigger. Okay, now these are for the most part torn from the ends of your chapters in your book, but some of you maybe didn't get a book, and that's kind of okay. But many of you did get a book, and so we have this. Okay. So this is, units, and it talked about units and doing dimensional analysis and things like that. Linda, we're just going to scroll a bit. There's a thing on significant figures. You don't have to worry much about the significant figures. I guess I have to scroll, or I can scroll. There, I'm scrolling now.
Yeah, everyone's screen is going to scroll individually.
Okay. So we get that, significant figures, and now I'm going to the next one. Now, I'm not focusing too much on significant figures, but my guidance to you is use all the numbers that are available to you. And round off only at the end of the problem, and don't round off too much. Okay, here's vector addition. It talks about how vectors get added. And you know how to do that. You know you have trig things. I'm going to go to the next, whoops, the slide keeps going. but nothing's there. So I'll go to the next slide. Now this is how we added vectors. And what happened is that we realized that to find, we had an AX, and I guess I'll make that bigger so it'll look bigger. So we had an AX that looks like A cosine theta, and an AY that looks like A sine theta, where theta is the angle that you're making with the X axis. And we know the length of the magnitude of the vector is A sub x squared plus A sub y squared, whole square root of that. That is the magnitude. And to find the angle, we often use the inverse tangent. Okay. And so what we could do is, and I guess if I go down to the very bottom of this, there's a thing and it shows you that you see you got a vector A and you're breaking it into components, the X component and the Y component, and that's how we learned how to do vectors. Okay, so that takes care of chapter 1, I think. It does. Chapter 2 was about displacement and velocity. And so we talked about average velocity in the x direction being delta x over delta t, and that was what velocity was. We also talked about acceleration. And acceleration, this is the next slide. Linda, I am advancing those slides, yes, for the students?
Yes.
Okay, great. Okay, acceleration was the change in velocity divided by the change in time, and both those are vectors. They have magnitudes and directions. You might remember that problem we did about a particle moving back and forth, and we talked about areas and stuff like that. That was kind of an interesting problem. So you see, when I'm talking about rectilinear motion, I'm talking about that. And in fact, here's some more equations dealing with motion with constant acceleration. So we have these 3 equations that are showing up on the next slide as 2,6, 210, and 211. So those are all equations that you can use to solve something. Okay. And we talked about proportional reasoning too a bit. Okay, and then we also talked about free-falling objects, and there is free-falling objects. And again, we're just rewriting the same kind of thing, but one of the things that we learned was you could go up and you could go down. So the motion of an object tossed up and down, you've got a U-shaped path, but in 2 dimensions we learned that that was all the same. So again, these are your grace notes. Linda, I think I'm going to number slide 9 now. And slide 9, it talks about the fact that velocities can be relative to each other. And we talked a bit about that in the class. And now I'm going into, this was chapter 1 and chapter 2. I didn't.
Okay, my time to shine. Obviously, there's a lot of notes here. I would highly suggest that you guys do not wait until the exam to look over these thoroughly. Honestly, it's probably a really good thing to study from, but you want to be familiar and you want to be able to find things. Yeah, I'm not sure where Bradley went. I'm sure he's going to be back any second, though. Any questions on the grace notes so far? Yes, Dimpy.
So in the email, I can see that there are some questions for the notes, and so there are some solutions as well in the going down. Is the solution for that questions over there, or it's a different thing?
So you're talking about the previous PowerPoint that we were on, right?
Yeah, the one that Bradley emailed all of us, and it has some
Yeah,
questions
so the
as well.
solutions are included at the end of the PowerPoint.
Okay, so I was just making sure that they are the solutions so I can practice it by my
Yes.
own. And this is gonna help with the preparing for the exam as well, right? Like it's kind of example for whatever study guide that you gave us.
Yeah, this is basically your study guide.
Okay, thank you.
There he is.
And Linda, you just took over talking, right, and stuff?
Yeah, pretty much.
Okay, so you want to keep doing that, or where are we? Okay, you were chapter 3. Did you finish talking about this, or?
I mainly just told them, like, it's a long study guide. It's a long set of grace notes, so they need to familiarize themselves with it before the exam if possible.
And that's certainly a good thing. Okay, we talked about this in 2 dimensions, and then the important thing that you remember is that that in projectile motion, the x direction is independent of the y direction. But we do have these equations again about that, and you see it is independent here. And we did do problems with projectile motion, and there is a projectile motion problem, and I think it's tied in with the density problem. But anyway, there is one of these things. So that's one of the things that you have. And I'm spending too much time on this. We really didn't cover uniform circular motion, but force was a vector, and so you have all of these things about force. And we had Newton's 3 laws. This one said that the net force is the mass times the acceleration. And we learned the difference between mass and weight. And that's something that you'll have to be able to do in Newton's 3rd law. And we drew free body diagrams. So anyway, you have all of these kinds of pictures. And we talked about what it means to be in equilibrium. That's when the forces are balanced. And we did problems with that. We also talked a little bit about friction, but not a lot. We did talk about some kind of forces, though, and one kind of force was elastic force, and that was if you shoved, something in against a spring, what happened? Again, I was supposed to cover this, and there is a problem dealing with elastic things, so make sure you understand that. And we also talked about energy was the same thing as work. They both come in joules. This was chapter 5 in your book, and we talked about kinetic energy. Being 1/2 mv squared, and we talked about gravitational potential energy being mgh, and we talked about elastic energy being 1/2 k x squared, where that was the spring constant. So there's a lot of things there with that, and there is a problem on conservation of energy, which involves those things and these as well. We did some things in chapter 11 dealing mostly with pressure. Pressure was perpendicular force per unit area. And we did some problems with hydraulics and things like that. And we talked about waves, where things look like sine waves, and simple harmonic motion gives rise to that. And we did a problem with intensity. Now, this was the problem where we talked about logarithms. You see, here's the equation right here in the middle that is about the decibels, and there is a problem involving these equations here. They're provided there for you. Oh, and here we also talked about beat frequencies, and I was talking with a student in my office hours. I think it was, wow, it's hard for me to remember. It might have been last night or it might have been early this morning. But anyway, they realized, they said, oh, the Doppler shift really is a beat formula. And I said, yes, it is, because they were correct on that. And here's the general Doppler effect that's up here. I'm going to make this one bigger for me, because the Doppler effect, this is the general master Doppler equation. But one of the things we learned down at the bottom of this is that there's a simpler equation where we say that the Doppler shift, this is kind of the ultrasound equation, the Doppler shift is equal to 2 cosine theta times the transducer frequency times the velocity of whatever it is. In your practice, it generally will be blood, divided by the propagation of speed in soft tissue. That's actually usually a simpler equation to use. I know Linda encouraged students to use this equation instead of the more general one just because it's simpler. Linda, you want to say anything more about that?
No, I think that covers it.
Okay, we keep going. We're almost finished with this. Here was density equals mass over volume, and this is pressure relating to that. This talks a little bit about Bernoulli effects and things like that. And then this is where we're talking about reflection, refraction, and total reflection. So here's a picture of what we studied. So the angle of incidence is the same as the angle of reflection, but then it gets refracted, and you have Snell's law working here. Now here's one equation that you had for Snell's law, and this was the sine of theta A over the sine of theta B is equal to, but this is the inverse index of refraction of medium B over A. So you see the A's and B's are in different places, but down here I just said, but this is also equal to, and this is VA over VB, and that's the equation we reviewed just a little bit earlier today, and there certainly is that as well. And that's the end of the Grace Notes. Okay, so that's what you'll have as Grace Notes. You'll also have access to the on-screen computer, and you also will have access to Excel if you want to use that. And so those are going to be your primary tools, and that's what we're going to be doing. Now, Linda, I think all right. So any questions about the Grace Notes? But that's what they are. And someone asked about that, so that's why I compiled them ahead of time. Okay, I think people are good with that. So Linda, let's go back now to the slideshow, and we're going to do some problems. Okay, now what we're going to do is we're going to look at problems, and I'm going to ask you to do them. And Linda, I'm going to let you pick because I think I put 2 problems here.
Let's do 41.
41 she wants to do. Okay, so I'm going to read 41, but here's what we're going to do. And Linda is watching a clock, and Linda is also going to have a poll out there when you're finished. And don't say you're finished now, because I want you to really use the Grace Notes that I provided and think about doing this. And this is a conservation of energy problem. So I'm going to read it. And the other problem, you'll have solutions there, and so you can do this. So we're going to give you time to actually solve this. I got to tell you, this really is very good practice. You see, if you want to become a good soccer player, what you do is you go out and you play soccer a lot, and you'll get good at soccer if you play a lot of soccer. So if you want to be good at this, you'll practice some problems. And Linda picked this one. So a 25-kilogram child plays on a swing, having support ropes that are 2.2 meters long. A friend pulls her back until the ropes are 42 degrees from the vertical and releases her. What is the potential energy for the child just as she is released compared with the potential energy at the bottom of the spring? Number B, how fast will she be moving at the bottom of the swing? And how much work does the tension in the rope do as the child swings from the initial position to the bottom? Okay, so you've got a mass of the child and things. So everybody, give this a little bit of a go. Linda, why don't you set up a poll for students to say, you know, if they're finished or yes or no, or what does yes mean? I'm done?
Yes.
Okay, now this, you're driving to an answer, and that means, okay, I would move on to the next problem. And you don't want to necessarily do that. I mean, you want to do some work, see if you can do this, because I've given you all the Grace Notes and everything else. And Linda has kind of a mental clock. So you're working on this. This is practice on conservation of energy. So give it a go. And Linda, you'll figure out whenever we should look at the solution.
Yeah, I'm thinking 658.
Okay.
And you know, if you guys get stuck, feel free to write questions on the slide. If you guys have finished part A, then can you hit the yes for me? All right, I'm going to call it because only 4 people have finished part A.
Okay, and that's fine. Now, Linda, I think these are at the tail end of the solutions are there towards the back. So,
Yes, they are. I will jump there in just a second.
okay, good. Now, one of the learnings here is, wow, the clock's going to be running when you're there, so you've got to wisely do what to do. Now, this is 41, and let's see. I don't know if I'm pulling that down or not for everybody, or if they all do their own. Everybody go down to 41. And Linda, can you point at this?
Yes.
All right, why don't you point at this and I'll kind of read some things. All right, let's look at the picture first, okay? So there was this swing and it had I guess a little girl in it. And the length of the swing chains were 2.2 meters, and you pull the little girl. I don't know if it's a little girl or not. I forget the problem. But anyway, you pull whoever this child was, you pull them back, and what happens now? So what happened when you went from the bottom position down there where the kid was sitting when they first mounted the swing, and they went to the other position that was up there? Well, what happened? Well, what happened was it increased the height. And so that's going to be MGH, which is, and you can kind of see that up there, Linda, across from the 7.41, it says U. So you see that's what you get. So that is going to be MG, and then that distance that you went up higher is the Y, okay? And then when you let go, what happens is that amount of potential energy becomes kinetic energy. And Linda, maybe we can point that over here at maybe underneath the 741 again. But it says, so the kinetic energy is 1/2 the velocity squared, and that's equal to the change in potential energy. And so that's what we get, is those two things are equal. Now, when you look at that, the m's are on both sides of that equation, so they cancel. You know what G is. We'll talk about that, Nishi, in just a minute, okay? In fact, I'm maybe going to let Linda talk to that after I do this, if she's willing. But the M is on both sides, so that cancels. And you have to figure out what the Y is, to start with, but then you have that, so then you just solve for v squared. So Linda, I'm going to turn it over to you, and you can talk about the solution there. And guys, I don't know how big you made this, but the way I made this, I had to scroll over there to see everything Linda will point at. So Linda, you good to go?
I'm going to give it to you.
All right, that's fine. All right, so I'm pointing. Linda, can you see my pointing? No.
No.
I need to go find a pointer here. I have a pointer now, okay? Now, and so you want to be where I am. All right, so the figure shows the difference in potential energy at the top of the swing is proportional to the height difference. So you see, you increase the height, so you increase the potential energy. And when you looked at this, the whole swing was 2.2 meters, the whole chain, but this part of the chain right here, this is a right triangle. There's the right angle, and that was 42 degrees. So you see this side going from this place where I'm pointing up to here was 2.2 meters times the cosine of 42 degrees. Okay, so that is what we do then. So this is going to be 2.2 minus 2.2 times the cosine of 42. Now, if you plug that into your calculator, Nishi, you asked the question, that's why I'm asking you, answering it. So if you plug cosine of 42 into your calculator, you'll get a number here. 1 minus that number times 2.2 gives you 0.56 meter. So, and Nishi, you're saying it is good with you, yes? Oh, well, look, oh, all right. So the question was asked, where is the 1 minus coming from? The whole thing is 2.2 meters, yes, from here down to here. But the distance that you increased is this one. And this distance up here, because of right triangle trigonometry, was 2.2 meters times the cosine of 42. So you see this whole thing is 2.2 minus this number. Now, if I were to distribute this, I would get 2.2. She's saying she got it. I'm going to just finish it, though, for other people. So it is 2.2, and then it's minus 2.2 times this, and that's where you get the 0.56. So you see the difference in potential energy from down here to up here was 25 kilograms. That's the mass of the kid, times g, which is the acceleration due to gravity, and this is the height, the difference in the height. And so that's the formula. That's the mgh that we had up here. And so that's going to be 140 joules if you multiply all that stuff together. Now I want to pause and see if there's any more questions. And Nishi was asking some good questions. That was fine during that. But are there other questions? Are we okay with this? Okay. We'll go to part B. Now, part B, you see what happens then is all this potential energy, this amount here, was changed into kinetic energy, okay? And so what's going to happen is we have this equation, 1/2 mv squared is equal to mgy. Now, that's g times y, and this is g times y. But we're going to have to solve that. So if we solve that for v squared, we're going to multiply both sides by 2, divide both sides by m, and take the square root, which is what we get here. And so if we do that calculation, we get 3.3. And the tension is radial and so there's no component of tension along the displacement, and the tension in the rope does no work on the child. These are really the more of the conservation of energy things that we're talking about. So any questions on this, or are we okay with this? So it was about conservation of energy. Potential energy was changed into kinetic energy. Okay, Linda, let's go back to another kind of problem then. Now, the other problem that is listed there, that's a good one for you to practice, and you may want to go visit Linda's study session or my office hours or something if you have questions on those. So, Linda, let's go all the way back to the slide where we finished with conservation of energy.
Just real quick to answer that question, these problems are similar. That's why they were picked out. So these are very relevant to what you should expect for the final.
But they're not identical, and students should not
Yes.
expect that. So, okay, so let's go up to then, Linda, this one. I think we're really finished with that. And I did pick these because they're similar. And what you might even want to do is you might even want to do some other things. Let's, Linda, and I know I'm being somewhat directive here, but why don't we look at problem number, let's look at problem number 37.
Okay.
And I'm going to read it. A beam of light in the air makes an angle of 47.5 with the surface. And it says not the normal of a glass plate having refractive index of 1.66. What is the angle of the reflected part of the beam and the surface of the glass? And then it also asks, what is the angle between the refracted beam and the surface, not the normal of the glass? So you see, this is a little bit, I mean, they're being very specific about what they're asking for here. So Linda, let's go try to find 37. I think you found it somewhere. Oh, wait, I don't know if somebody just left or they were asking a question. So we're going to 37, the solution to 37. And there it is. Okay. Now, the angle of incidence then, you see, and can I draw on this, Linda?
Yes, you can.
Excellent. So let me do that. Okay, so we had a surface here. I'm going to draw the surface like this. We had a surface, but we had an angle of incidence here. But this was this angle, 47.5, was the angle it made with the surface. So you see, this is the 47.5 angle right here. That's 47.5. But as you all know, we always take the normal to the surface when we're using Snell's law. So you see, this is the perpendicular to the surface. So if this is 47.5, this is going to, or excuse me, this is 42.5. This other angle is going to be 90 minus that, or 47.5. So you see the angle here is 47.5. So that's the angle that's there, and that's the angle that is in Snell's law. Okay, so the light reflects from the air into the glass, and we knew that, so the air over here in was equal to 1, and in the glass it was n is equal to 1.66. Okay, so you see, here's what we need to do is we need to, and this is Snell's law with indices of refraction. So NA times the sine of theta A is equal to NB times the sine of theta B. That means that the sine of theta B, this part, is equal to NA over NB times the sine of theta A. So we take the ratio of the indices of refraction that we have up here times the sine of this angle. And it looks to me like they actually, no, that's right. They did it right. This is the 42.5 is equal to 0.407. Now that means that the sine of theta B is 0.407. You have to use the inverse sine of that. So what you're going to do is you're going to take, you're going to use your calculator, you're going to take the inverse sine of 0.407, and it will tell you that theta is equal to 24 degrees. Now, that says that the angle that's refracted here is going to be 24 degrees, so it's going like this, or actually it says this one is 24. I got to figure out how to erase that. I can't erase that without erasing the whole thing. But anyway, so what we're going to do is this is the angle for Snell's law. So this is the angle to the normal. And so the refracted wave makes what kind of an angle? Well, it's the other angle that they're talking about in this problem. So that's going to be 66 degrees. Okay, questions on this, because again, this was a pretty straightforward application of Snell's law. Okay, someone's asking a question. Let's see. In the exam, are you going to ask angles from the surface, or I don't remember what angles? I'm going to guess that I probably am asking angles to the normal, but I don't remember. Linda, do you remember?
Not off the top of my head.
Okay, but you read the problem and you see, but realize that Snell's law is only with respect to the normal, and you see how that was an important thing in this problem. Okay, they said that's good, thanks. Okay, excellent. Okay, Linda, let's go back and let's look at another problem. I do know what time it is, guys, but that was a Snell's law problem. You got some others, so we're going all the way back there. Here are Newton's laws in vector problem, and again, we don't have a lot of time, but we're to find the tension in each chord. Now, I think, if I grab my pointer, I think you can see me pointing. Let's just talk about problem A. So you see you got 250 newtons, that's this weight pulling down here, but it's being supported by this and this. So what's going to happen is you want to know what's the tension in each chord. So you want to know, well, what's the tension in this chord and what's the tension in this chord? Well, the upward forces, since this thing isn't falling down, the upward tensions have to have this in equilibrium. So the upward components of this are going to add to 250 newtons. And since it's not moving side to side, it's being fixed there, the horizontal components are going to balance each other. And we're going to use trigonometry. And if I were to draw this, which I'm going to, that's going to be a 90-degree angle. So you see this is a trigonometry problem. Now, Linda, let's please go back to 13A.
Okay.
Okay. Okay, so you see this was the weight that was equal to 250. That was the tension going down, but then the sum of the two going up has to be equal to that 250. So you see, and they have to add to 0. So in the y direction, then you're going to say 250 is equal to the tension in A is it is 0.866 because this is the upward component of this. So this is going to be the cosine of 30 degrees, which is that, plus the tension in A, but that's going to be let's see, that's going to be the, it'd either be the sine or the cosine. It's the, let's just say it's the cosine of 45, or no, it's rather, excuse me, it's a sine of 30. And so that's going to be TA. We add those two together, that balances with the 250. And then I say, oh, this direction, which is TA times cosine 30, and is equal to the negative of TB times sine of 40, or sine of 45. You set those equal, and you have two equations and two unknowns. So you can solve those two equations and two unknowns for TA is 186 or 183 newtons, and TB is 224 newtons. Now I am going to ask you a vector problem on the test, and we did other kinds of vector problems, didn't we? Linda, maybe you remember the thing where we had a person's foot.
Yep.
And we had some kind of thing going on with a person's foot. and there were vectors, and we said, oh, you had to have things. Those are good problems. Other good problems that are vector problems that we did as well. Okay, so Linda, let's go back to the early part of the slide. We're almost ready to wrap this up because the day is almost over. Okay, so we talked about that. I have some other examples here, and these go down. And Linda, let's just go through the slides. Here's one on attenuation and intensity. Let's just go to the next slide, Linda. Rectilinear motion, there's one. Dimensional analysis, there's one. And maybe that's all I did for today. That's all I did for today, but that was about half of an exam. So anyway, we'll do some more of this. If you guys have questions on this, you should ask them either at Linda's help session, Tom Topol's help session, my office hours, or with classmates, or just in your own studying. But you have these things to study, and we will do more problems next time, either answering questions on this or doing some more problems that are similar to some of the others. Okay, Linda, anything else, or are we good?
No, we're good.
All right, I'm going to be in my office hours in a bit. It is the most recent, and this is pretty recent, when I changed that. In fact, it might have been last night when I changed it. So you won't have to look very far in the announcements to find it. Okay, good night, everyone. Please be careful and prepare well. You all will be fine. Take care.
Have a good evening.
Good evening.